Okay, so good morning. So we continue our discussion on this. Uh, Basically, we are discussing now non-parametric methods of Bayesian classification, and there we discussed about the uh, classification uh, classification problem earlier, where we can see that how this non-parametric method, using non-parametric method, you can compute the probability density functions and use it for Bayesian inference. Now, in a typical non-parametric method, we discussed about the k nearest neighbor method. Today, we will consider the extension of that method for solving the regression. So, as you know that in the regression, uh, here the target function is in this form. In a classification, you are mapping to a set of classes, whereas in regression, you are mapping an input to a value, real value, right? To a value in the real space. So uh, there, it is defined in the form of a function. As you see that uh, if I give you the true target function values for certain instances, like in the same way, the supervised classifier where we specify the labeled samples, where each sample has a class label. In this case, you have a functional value in the real space. So the representation is like this, that you have the x superscript t as the tth sample, and the respective functional value is f of x superscript t. So we consider, say, ith neighbor of x is xi. So ith neighbor in the sense that from the ith nearest neighbor, right? So it should be ith nearest neighbor is xi. And then one very simple way of doing regression is that you can take the average of all the functional values within the k nearest neighbors with what are available to you, and you consider that is the function value itself, though it's a bit crude, but no, it is a simple method, but it works in many cases. Of course, there are improvements, so that we'll be discussing. So one of the improvement is that instead of taking simple average, why don't you take an weighted average, where weights will be proportional to the inversely proportional to the distances from the sample. That means the first nearest neighbor will have more weight, second nearest neighbor will have, after that will have the, in the next ranking of weights. So in this way, you can define a weight which is a function of distance and which is an inverse function of distance from the sample x, from the instance x to the. So that is what inversely proportional to square of the distances that we consider in this case as the weight. And we can also consider it, because you know that kernel function, we have seen it's a function of distance. It's a so you can use the kernel function, and in the kernel functions, the characteristics is that the kernel function dies down as the distance increases. That means it is a monotonically decreasing functions of distance. So and mostly it is actually the square of the distances, right? Inversely proportional to that. So that's why if you use kernel function, it's just proportional term. Instead of specifying with distance function directly, you can use a kernel function and use it as a weight. So that is a simple way of doing regression using k nearest neighbor, no, k nearest neighbor principle, which is very similar to what we did for class assignment also. Now, there is another technique which is called locally weighted regression technique, and there what we consider that we locally fit a rather what we consider that there is a global function, of course, but its variables are locally fit. So you have the target function, which is linear or on attributes, is a global function. So since x is of d dimension, so your target function, if it is linear of attribute variables, we can represent it in this form. You should note that the term linear is bit relaxed here because you have a constant term w naught here, which does not make actually the function as linear. It's affine. But no, in the homogeneous space it is linear. So you should understand these subtle differences because these are very important when you understand a linear operations, right? So in a very simplistic way, we call it linear because no, it does not have any polynomial of degree 1. So that's the kind of thing we call it as linear. So a loose definition of linear function. So anyway, so if this is the functional form, so what you have to do, what is your problem of regression? Can anyone tell me that what should be the, how can we define the regression problem with this functional form? So was there any response? So did you, so Rahul Kumar, can you answer this question? So probably Rahul is not there. Ritoban? I don't find Ritoban also there. Deepak? So I'm not sure whether people are there. No response. Okay. Ashwini? Hey, Ashwini? Yeah, please. Can you no. Can you answer this question?
No, sir, I missed it. Sorry, sir.
Okay, so just let me tell you, regression problem, it's a very general definition for a regression problem, which means that if I give you a functional form and if I give you the corresponding level or corresponding sample data, where there are data points where the functional forms are given, like the previous case of regression you have seen. So the regression problem is that what is the best fit of this functional form with respect to that data. That means you define an best fit error, and then you have to compute the set of coefficients which will minimize that best fit error. So that is one way of formulating this problem. You might have gone through the least square error estimates. I'm sure you have gone through those things in your basic courses. So those techniques are used for solving regression problem. And actually those problems are defined in the framework of regression. So that is what is regression problem here. So we'll be also considering a regression problem, but it is a locally weighted regression, which means this function could be also piecewise, continuous, which means you can have a uh, uh, local fit around x. So you can find out, for example, k nearest neighbors, and you can have a local fit of this function using those nearest neighbors, and estimate the functional value. So at each time, you have to really solve this problem using, for example, say k nearest value. So you can define an mean square error no, error criteria, and it could be of 3 scenarios using k nearest neighbors. Say the error criteria could be given in this form. That means it's an weighted uh, square of errors, right? Weighted square of errors, and you see that this is very common trick that if you are using the square of errors, you add an coefficient half 1/2, just to know if you take the gradient, you know that to solve this problem, you have to you have to use the gradient of error with respect to individual weights, individual parameters. And basically, instead of equating 0, numerically you can solve it by following a steepest gradient method, because analytically you are not going to get any particular equations. You can of course use least square error estimate, and that also is possible, but no, in this case we'll be following that steepest gradient methods. We can see that. So if you have over unweighted k nearest neighbors, then you can simply ignore the weight coefficients in this form. So this you can ignore, right, for unweighted one. Right, and so overall training examples with weights proportional to k x xt. It could be overall training examples, then it's a global function. Otherwise, no, if we consider a local window also, you can have every local window, you can recompute and you can do this. So then it becomes local. Over k nearest neighbors with weights proportional to k x xt, as I mentioned there. So weight update rules for minimization, where you follow the steepest gradient method. Please look into the literature, look into your book. What you are doing basically, you are starting with any initial parameter set, which are here wi's, and then you update this parameter set following an update rule, which means you are basically adding this. This is actually negative of the gradient of the error function E. So negative of delta E, delta Wi, and then there is a step function, step value, that is eta. That's a hyperparameter. So you simply add for each Wi. That is what you are doing. You are simply adding at each iteration, say Wi plus this value, negative of the gradient, proportional value of the negative of the gradient, and you go on iterating this till Wi's get stabilized. So there are proofs for the convergence for convex functions and other things. So so this is the method which is used to get a locally weighted regression function and use it for your prediction. Any questions? So with this, let me summarize the non-parametric approaches. Like we have seen how parametric approaches are dealt with. So in the non-parametric approaches, as I mentioned, that we are estimating again the probability density functions, but without using any parameter. What we are doing, we are using a kernel functions. So every data point is used for estimation of that probability density function, and it should be kernel function is defined such that it has a local support, and it has a bounded integral value of 1. Naturally, since every time you are using the whole data set, training data set or input instances, so it requires high computation and also storage. But it's very simple to implement, and also it provides good performance on the average. You will find that many cases, k nearest neighbor classifiers are giving the very sometimes they are giving even the best performances against all other kinds of classifiers. But the catch is that they are very computation intensive and they are also storage intensive. So they are not efficient, and there are also outliers and other errors are also problems will be there. So it can be modeled as instance-based learning. So with this, actually, and as you see that possible to use in regression. So with this topic, we have covered, and if there is any questions, let me know. So I will basically take a 2 minutes break to to start the new topic. So I'm coming back after 2 minutes after organizing my slides. Thank you. So let me start a new topic, that is on unsupervised learning. So far, we discussed about supervised learning, as you have seen that where we have learned using the label data. We have learned a classifier or even a regressor using a label data. So the problem was that you have to learn a mapping from the input to an output, and the labels are provided by a supervisor. So these are the examples where you can classify, you can regress. We have discussed about these examples. But what is meant by unsupervised learning is that no, you are learning only from the input data. So no such levels are given. So in fact, the problem is not the same as the supervised learning. It is you are not trying to then map anything because the mapping, there is no concept of mapping here. Rather, the concept of grouping will be more relevant. So I'll be just elaborating that part. So that is how we define the unsupervised learning problem. So as I mentioned that no levels or instances are available. So there is no supervisor to provide the mapping between input and output. So what is the objective here? Objective here is to find the regularities, structures, or patterns in the input. So which means no, you are trying to find out groups or partitions in the inputs data which have certain kind of similarities or some kind of regularities in them. So there are, of course, various questions in unsupervised learning that arises that when you do not have any such information, then no, what is the starting point? For example, if I ask you to find out the groups, so should we have at least some Q? What should be the number of groups? That may come from some other domain, some other knowledge from some other, no, not from the data, from the domain itself. Uh, you know already that there exist so many groups, and given the data, you are just trying to associate different samples within those groups. So number of clusters. So these groups are called clusters in the jargon of unsupervised learning. Whether there exists any hierarchy among these present among them, that is also another question. Say, when you are considering the groups, so whether you have certain kind of hierarchies in that group. And how to attribute them with semantics. So once you have a group, then how do you characterize those groups? That is another question. So there are different questions. These are some typical questions that we try to find out, we try to answer in this process of learning. It is not only the grouping, it is also those associated questions regarding those groupings. So the clustering, that is a very well-used term, and that is the essence of unsupervised learning, if I say, very core concept of unsupervised learning. So the clustering means it's a task of organizing objects into groups whose members are similar in some way. So you see that this is the kind of loose definition of similarity. I mean, it is not very hard definition of a cluster. So it's a collection of objects similar to each other, but dissimilar to the objects belonging to other clusters. So that is another another point you should also remember. The groups are not, they should be also distinct. So which means among the set of groups, there should be some distinct characteristics to attribute it as a separate group. So regions of homogeneity in an image. So that is one kind of examples of this kind of unsupervised learning, which we call segmentation in the jargon of image processing. Our grouping of similar components, and that is in fact the cluster. So one, it's a very simple example about this group. Say you have this image. Now this image is the image of a mushroom over certain kind of black biomass. Okay, and so you can see that you can have this kind of two types of objects, mushroom and the biomass, ignoring the other presence of other objects. Primarily, these are the two objects in the scene, and it is not that those regions are also connected. I mean, so there could be several, but overall there are two such objects, two such clusters. So, so the definition of cluster, it can be also well understood if I consider how it differs from a class. So when we say it is a class, it's a well-studied group of objects identified by their common properties or characteristics. So class is a very well-studied, you know its property, and that's how you determine whether an object belongs to that class or not. Whereas a cluster is a group with loosely defined singularly determined objects. So, and it is a potential to form a class. So it is one step before declaring something as a class. So unsupervised learning is a very powerful tool of scientific research, because when you do not know anything, you are starting from scratch. First thing, given the data, you try to see that what kind of groups are there, and then you keenly observe that whether they have certain kind of meaning or semantics associated with your domain, and accordingly, you try to then characterize them, identify. So all these research or pre-scientific or in the science in investigations, the very beginning of any particular domain. Now this is one thing has been studied. You call it particularly this life bioscience, where different species, etc., they are studied and their relationships, their grouping, those are also carefully studied and they have been attributed. Now, when we are trying to do it from the data distributions point of view, so this we do it by using certain kind of logical framework, by understanding the characteristics, etc., and then you start building up your groups based on those properties, and various ways you do it in the scientific research. But no, in the machine learning perspective is that you have simply data, which is a distribution of points in a space. So there, you are trying to first understand from that distribution what kind of structure is there in the space. So the clustering, there are different motivations. One is that finding representatives for homogeneous groups to reduce data, discovering natural groups or categories, so to describe by their unknown properties, finding relevant groups, major groups in the given context, segments of an image, for example, detecting unusual data objects, which is kind of detecting outliers. So this thing. So today I will discuss one of the very popular methods of unsupervised, or rather I should say clustering. Now let me call the term clustering directly. So very popular method of clustering, a very well-known method, and this is called k-means clustering. So algorithmically, it is very easy to understand. So you need to also understand its theoretical perspective. So let us first understand what is this problem. Once again, the problem is same as the clustering problem, but no, we will put some more constraints on that clustering problem. Some more prior knowledge will be given. So this K stands for the number of clusters that is given to you. So K means clustering. So K is a hyperparameter, which stands for the number of clustering. In fact, it came in the name itself, it has been associated. So we call that the name of the parameter is K. So compute K partitions in them so that it minimizes the sum of squares of distances between a data point and the center of its respective partition. So this is the criteria of grouping. This is the objective. If you can get that partition which has the minimum sum of square of distances from its center for each partition, then we say that is a k-means clustering, partition of the k-means clustering. So this is an optimization problem. As you see that we are minimizing the sum of squared errors, and this can be mathematically expressed in this fashion. Say you have the input data point represented as x, and if I consider there is a partition, so this error is defined, sum of squared error is defined with respect to a given partition. Suppose there is a k partitions. So consider for individual partitions, whatever element belongs to that partitions, take the sum of squares. So this term take the sum of squares of its mean. So this is for an individual partition, right? You are taking the sum of square from the mean. So this is the mean. This is CK. This is the mean of that partition. Okay. So then you are considering sum of all such sum of squared of squared errors. We call it sum of squared errors. Overall sum of squared errors. So your objective is to find out that partition which will minimize this error P. Any question at this point?
Sir, we have to find out the mean square with respect to all k partition for a single data point.
Actually, that is what? Not a single data. No, what is a single data point? Where is a single data point? What is your understanding of single data point?
Sir, I mean that we have different data points in our data set. Then and we are partitioning this into k partitions. Then we have to find out the mean square with every for a point, single point to every center of k
No,
partition.
not every. Only that data, only the data point which belongs to that partition. You see that expression. This expression, you are taking sum of square between the data point which belongs to partition, into that partition. Let's say it belongs to kth partition. So you have to take only a small k here. Huh? So there is a little bit of no. You should understand the big k is for that number of clusters. So, so this is what it is not all. So let me give you an example. Suppose you have say these are the 4 data points, and you define a partition. Say suppose you define this partition and this partition. So how do you compute the sum of square root of errors? Compute the mean of this partition. Suppose this mean is here, okay, and compute the mean of this partition. Suppose this mean here. So find out the squared errors from these samples with respect to this sum, with respect to this mean, and sum them. Find out the squared errors from this point, sum them, and sum of all these will give you this total sum of squared errors. Is it clear?
Yes, sir.
So you have to find out that first partition which will minimize it. There are many other partitions, no? So this could be another possibility. So there also you'll get some squared error, sum of squared error. This could be another possibility. Say this and this. There also you can get sum of squared error. So out of them, which one is minimum? And that should be the result of your cluster. You should consider that cluster. That partition is your answer. So naturally,
and sir, can one data point belong to 2 clusters?
No. Partition. See, the definition of partition means they are all disjoint. So they are all disjoint and they cover all the data points.
Okay, sir.
Okay. So fine. So as you can see that you can do it exhaustively. You can enumerate each and every combination. So each partition is a particular grouping, and you can compute this sum of squared errors, and then you choose the one which is the minimum. That is an exhaustive k-means algorithm. But the number of ways you can do it, it's basically exponential. So if I do it, it will come something like this: k to the power n by k factorial, very close to that. And as you can see that the order of it is exponential order of n. So that's why it is basically prohibitive, right? And it can be shown it's an NP-hard problem for k greater than 1. So there is a very simple algorithm that I will be discussing here, which will which may not give you the optimal solutions, but which will give a good solution. Okay, which means in most cases it will give good solutions. We can say near optimal, but I'm not saying, because when you say near optimal, also there are bounds, etc., that you have to define. That you have to find out. But here in fact, there are analysis. K-means algorithm is a very, there are many analysis of K-means algorithm. You can see those analysis very interesting, and there are certain bounds in certain context. But in general, if you are not using those from the very generic K-means, these bounds are not very precise. So given K initial centers, what it does, this algorithm, let me describe it. I have also figurative description. So, but here, let me just simply give a summary. And one of you, I will ask one of you to summarize. Please note it carefully. So what we do here, we consider K initial center. Suppose you have some data points, as I was telling you, some data points. Say these are some data points. I'm giving it with respect to 2 dimension. In fact, later on my slides also have this example. So you start with, say, let us consider value of K is 2. So let us consider that we have a mean here. This is my initial set of means. So this is 1, say this is 1. I do not know how the distribution is. You can look at it and you can choose a mean. But no, given a problem, naturally, these are all random points. So we can choose any initial centers, any points which are assumed to be your K means. That means this many means are actually centers. So centers of class, they are representative of those clusters. So means are representing clusters. So they are representing clusters. Now you are defining the sum of square error. So first you do the cluster assignment of this point. So what is the cluster assignment? You consider for each input sample, which one is the closest. So use that one nearest neighbor rule in this case. Use the one nearest neighbor rule to assign to a cluster center, which means, for example, this one, which cluster center it should assign? It should assign to this cluster center. I'm naming them as C1 and C2. So this one will be assigned here. This one will be assigned here. In fact, if I, that mathematically, you can take the perpendicular line of this perpendicular bisector, all these points, they are closer to this. And all these points, they are closer to this. So geometrically, you can always tell that. But computationally, what you do, you simply compute the distances and find out which one ever is the less. In this case, 2, that's why I'm saying less. You assign that cluster center. So once you get this partition, now you recompute their means. So this partition, suppose this mean is here. So this mean will be updated to this place. Because you know that this is representing these clusters. So now this mean is updated here. And similarly, say this mean is updated here. And go on doing these things iteratively till there is not much of update of these means. That is what. So when you converge, you get a partition. Okay. So convergence is more or less assured, but sometimes you may get oscillations of centers, which are all good solutions. So, so that is a theoretical. I should say theoretical derivation. So in that way, you are not saying it is converging. So it may oscillate around the point. Anyway, but those points are near the converging point here of this algorithm. So now the task of asking someone who should answer me. So I could see here, let me see. Sagar Allahabad. Are you here? Okay. Sumit Bora. Sumit is not also here. Sanket Sharma. No. Bharat Sirusola. Abhinandan De. . So none of you are answering, no? So which means you are not attending classes. Simply join. Puneet Kumar Singh. Neha Dalmia. Bhuvaneshwari. Rupinder. Rupinder is also not here. Gautam Sharma.
Yes, sir.
So can you summarize, please?
So, sir, basically, first initially we will point any center. We will initially randomly set any center, and from C1, C2, let's say, and from those we will calculate. Let's say for any data point, we will calculate two distances from C1 and one from C2, and whatever the closest is, we will assign that data point to that cluster. So we will. So at the end of one iteration, we will have one data point assigned to one cluster, and then we will calculate the mean of one cluster, and then
Not
move.
one data point. Yeah.
Now for each one. For
All the data point you do it, and
Yes,
then
sir.
you get the outputs.
For
Yeah.
each data point, we calculate the distance, like say error from one to C1 and one from C2, and assign the closest one to it.
Right. Exactly.
And then we find the mean of both of the clusters, and then shift the center, and then repeat this algorithm.
Very good. Right. You are exactly. Thanks. Okay. So let me continue. Just grab this thing. So as I mentioned, that iterate above two steps till the centers do not change their positions. So this is that figurative example I am talking about. Let me quickly go through it. I have already explained, so I don't think you have to. I have to describe them. So these are all being shown. You can see with colors. The centers are shown here with triangles, and the colors are showing each partitions. So you are updating centers. Now this becomes a new iterations. Once again, you do the same task. You compute those partitions, update centers, and go on doing these things till you find that no, there basically not much of update is taking place. Now, this is when we are doing this convergence, what you get, um, it is, I mean, it is fast algorithm, but it is not necessarily causing better convergence. A conservative approach would be, as inadvertently, I think Gautam, you answered that you said that one data point I will and then update. Actually, that there is also an approach for that. What you do, you choose the best data point which will have the maximum minimization of the sum of square error, and you basically it will be changing of the cluster. So from if the data point by changing the cluster from ith cluster to a jth cluster, you find out what is the change of the sum of squared error and choose that transfer which has the maximum reduction. And you do that change, again recompute and do this thing. So it is computationally intensive, but no, it causes better convergence. That is why. So the strength of the K-means algorithms, it tries to minimize the energy function, as you see. It is a good analytical problem in that way, but of course we solve it empirically. So convergence guaranteed at a quadratic rate. As I mentioned, the convergence guaranteed, but there may be an oscillation. So it's a linear time complexity in order n, also dimension d and k. Now, though it is linear, let me warn you that for a large data set, this is very hugely, it takes huge time. So that is also another problem of K-means. And it's also versatile, simple, and invariant to data ordering. So the weakness is that it only detects well-separated, compact, hyperspherical clusters. you should get the value of k. It's sensitive to noise and outlier points as due to squared Euclidean distance. It may get stuck at local minima. Of course, that you understand that you can get a local minima, though the function in that case may not be convex always. So highly sensitive to the selection of the initial centers and improper initialization. So initialization sensitivity is there. So if you have improper initializations, you may not get a good result. So you may get empty clusters. So some of the clusters may be empty. Suppose one of the center is very far off of the data point. Theoretically, if I say, you can choose that, isn't it? Then all your points will be closer to the other center. So there is no, I mean, it is converging. That is the first iterations, and every point is assigned to the same cluster. So whatever you do, you will always get to the same answer. So the empty cluster is a problem if you have improper initializations and slower convergence and a higher chance of getting stuck in bad local minima. So I hope these are the things you have understood. Particularly the cluster shape should be spherical. So problem of K-means is that it tries to consider the shapes are nearly convex shapes, and also spherical means nearly convex shapes. So if there is a kind of say I have a distributions like this. So this is my one cluster, and say this is my another cluster. Say this is my another cluster. I mean, I have data point, chosen data point. This is my ground truth, for example. It is very difficult to get this kind of clusters extracted using K-means. So that is a spherical shape means I have clusters in like blobs. Huh? These are good cases to apply for K-means. So you should know the number of clusters, and also the cluster shapes should not be very arbitrary. It should have certain kind of blobbiness or some kind of spherical. So there are various methods by which we can overcome some of these limitations, or we can try to reduce these disadvantages. One of the thing, say initialization is one issue, that so you can use some adaptive initialization method. Like you can consider that each point randomly you can choose to one of the clusters. So basically, instead of choosing centers arbitrarily from any point in the space, you choose it from the data point. That's a simple approach. Randomly, you choose one of them to the clusters. Or first k points as the center. So instead of randomly, you just consider. So all are data points. You see that all are data points itself, and they're so which means that you are basically avoiding those situations where a cluster center arbitrarily could be very far away. At least they are within the data set. So sensitive to data ordering, of course, choose them randomly, and outliers still may get selected. Or you can do repeated k-means. That means you do number of times k-means and try to see that what kind of stable results are there. So you can have k-means on j random subsets and merge all centers. That means you take j random subsets and you perform k-means and merge all centers and run k-means repeatedly on them. So this method is very simple. What it does, it means that say, let me show you. Say I have some data points like this. Okay. So suppose randomly I choose some random subset. Say let me choose this subset, and I perform k-means here. And after performing k-means, I have two such points. Similarly, I can choose another random subset. I will perform k-means. I will have two more points. Because every time I will get k-means, so in this case, if k equal to 2, every random subset will give me these 2 points, and then you perform k-means on them itself. Then you perform k-means on them itself, and whatever is the result, that is your initial center. That is not your result. That is your initial center. Then you perform the k-means on the whole data point using those centers. That is what is repeated k-means. Is it understood? Any questions on this? So choose the best set of centers, minimizing the error, and use them for iterative convergence. So you can do various ways. So one of the I should say another popular extension of k-means, which is called k-means plus plus. This is used in many cases, and this is very popular as a variation of k-means. So what it does, let us try to understand algorithmically. So first center you choose randomly, that is the C1. And then next, for the ith center, you choose the center. Actually, the idea is that you should choose your centers, they should be well separated. So in a probabilistic terms, you are choosing it, you find out you are choosing always from the data point only. So you choose that data point with a probability proportional to the distances from the square of the distances from the selected minimum distance from the selected I minus 1 centers. So that is what. So it's a bit random. So your probability is defined in this way. So with this probabilistic probability distributions, you are choosing an element from the candidate set. So naturally, you see that you have to make the probability distribution as a probability. You have to basically normalize it so that sum of probabilities of all candidates becomes 1. So that's why the denominator comes here. So in this way, you are choosing it and then you are performing it. Performing the k-means after that, same k-means after that. So we call it as k-means plus plus, and there is a theoretical bound. You can read papers on k-means plus plus. You will find very good theoretical analysis on bounds from the optimal k-means. So let me stop here today. I still know in the next class also I will discuss about this part that k-means will continue this discussion. So today we are stopping here, and if you have any questions, let me know. So just to remind you once again that your next quiz will be held on October 7th. That's on Thursday. And the syllabus would be the topics, what would be covered till next Friday. Okay, so it seems there is no more questions. So thank you very much. See you again.
Sir,
Yeah, please.
sir, I have a doubt in k-mean plus plus.
Mm-hmm.
So I
What
am
doubt?
not understand how to take next center, next mean value. Px test you have find out according to the probability we are finding the next student center. That how we are
Yeah.
finding.
Do you know the random selection algorithm? How do you generate the randomly? How do you generate? If I give you certain probability distribution, suppose I have given you a set, and for that set you have the probabilities. For each element you have the probabilities. Actually, I can say for the number, and for each element there is a probability, and it's a finite set, and you are going to select one of them using this probability distribution. That there is an algorithm for that. You can generate any random number, and you can find out that at which point. Say you have to basically keep them in a particular order, and then you find out that what is the cumulative probability distributions. You get the cumulative probability distributions and see that that random number, whether it is where actually it just simply less than that number, where it crosses, and select that element. So please read this algorithm. You read an algorithm book where this is a problem. So if I give you a probability distributions for a set of elements, then how do you select an element following that probability distribution? Is it clear?
Yes, sir.
So read that algorithm, right? It's a simple algorithm. Read that algorithm using the generation of random number following an uniform distributions. Okay.
Okay, sir.
So you have those functions. Huh? So here also what you are doing, you are defining the probabilities of every candidate element which are not chosen yet by following this rule. So you can see that it is basically computing this probability. I hope these expressions it is understood by you. What it is computing the minimum distance of a candidate X prime from all the chosen centers so far. Suppose there are I-1th and you are choosing the candidate center. So you find out of the existing I-1th centers, what is the minimum distance? We are taking on a square of distances, right? So proportion to that, for every candidate element, it should proportion to that. Proportion to that, this probability will be different. So this is first defining that probability distribution. So it is computationally intensive. As you can see that every time you have to do it with the almost all the data points, n minus I data points for the ith center. You have to do it for n minus I data points. And then you select that center with this probability. Okay, so let me, as I mentioned, let me stop here today. And again on Wednesday we'll discuss. Thanks.